Hey guys, Miss Marusik here, and in this video we're going to talk about weak acid and base calculations. Now, in our previous video we looked at strong acid and base calculations where whatever acid or base that we had completely 100% splits up into ions, and so therefore we could use stoichiometry ratios to figure out the concentration of those ions, and then we could take those concentrations, plug them into either a pH or a pOH calculation in order to finish solving the problem. The issue is that with a weak acid or base, they do not completely split up into ions. They do not ionize 100%. Now, technically, the correct term for acids and bases is to say ionization, or that they ionize, because they are covalent structures that are splitting up into ions. However, some textbooks will still use the term dissociate or dissociation, because that's the term that we used with ionic compounds that did exactly the same thing. In any case, it doesn't matter which term you use. The key is that it's not completely splitting into ions. And so therefore, we end up forming an equilibrium between reactants and products. And so therefore, in order to solve these problems, we are going to have to utilize Rice tables and equilibrium expressions in order to get those concentration of those ions. So we're going to have to go through a little more work to get those concentrations before we can use pH and pOH calculations because of the fact that they are weak acids and bases. Now, when we're utilizing those equilibrium expressions, instead of using Kc, we're going to use Ka for an acid equilibrium or Kb for a base equilibrium. However, regardless of which of those you're using, it's still products over reactants raised to an exponent that's equal to their coefficient. Now, one of the other things that we're going to be able to do with these is actually calculate the exact percent ionization of our substance. Now, we know it's going to be less than 100%, but we can actually calculate how much less than 100% it's going to be. Something interesting is that usually for acids and bases that are weak, the percent ionization is very small. Often less than 10% of it is actually going to split apart into ions. Most of it is going to stay as the original acid or base substance. Now, there are formulas that we can use to solve these, and you notice those on here. These are not on your formula chart, by the way, so these are going to be ones that you are either going to have to get familiar with or memorize them, whatever you feel like is going to be best for you. Percent ionization is how much of our substance actually became ions over the original concentration that we had of the substance. So basically a part over whole scenario, just like we do with any other percentage. But in order to get that fraction into a percent, we would need to multiply it by 100. So if we have specifically an acid for that percent ionization, we would do the hydrogen ion concentration, or you could do hydronium up there. Remember, those are interchangeable, over the original acid concentration times 100. Or if we have a base, we would use the hydroxide over the original concentration of the base times 100. So with all that said, let's actually see some problems in action. So our first example here gives us a 2.50 molar acetic acid solution, which has an equilibrium constant of Ka equaling 1.8 times 10 to the negative fifth. And it wants us to determine both the pH and percent ionization of the solution. Now, I noticed that acetic acid is not one of these strong acids that we've had to memorize. Remember, we had hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, chloric, or perchloric. It's not on that list. I also noticed that they've given me a Ka value, which, let's be real here, they're not going to give you a Ka value unless it's a weak acid. So I know that this has to be weak, and what that means is that I know it's not going to completely split apart into ions. And so we are going to end up making an equilibrium here, and that means in your work you are required to show some sort of Rice table to show what exactly is going on with the concentrations of everything. So the first thing I'm going to do is I'm going to take that acetic acid and write a reaction for how it would behave in water. And so that would be the R in my Rice table. Remember, acetic acid has acetate in it, which is C2H3O2 -1. And I would have originally enough hydrogens to balance that charge out at the front, which means I would have one hydrogen in front here. And I'm going to put that into water. And what's going to happen is if we have have an acid, we know that it's going to lose an H+. It's going to lose a proton to the other substance. So that means here the water is actually going to be behaving as a base. And so when the water accepts that base, its conjugate acid ends up forming hydronium. For the acid of acetic, once it makes its conjugate base, we would end up with just the acetate polyatomic ion here. So then, initial concentrations. I would have my 2.50 molar of the acetic acid and 0 of both hydronium and acetate. Notice I crossed off water here. I didn't even bother with the rice table. And you're thinking, well, why did she do that? Well, remember, it's pure liquid. And so therefore, I wouldn't have included it in any type of equilibrium expression. And so I'm not really worried about any pure liquids in my rice table itself. So next, let's address the change. Because this is weak, that 2.50 molar isn't going to all go away like we saw with strong. Here, only part of it is going to go away. And so at equilibrium, I'm going to end up with 2.50 minus X here for that ending concentration. For the hydronium and the acetate, I can't assume they go up to 2.50 like we saw with strong acids and bases because it's not completely ionizing. It's not completely splitting into ions. So these are only going to go up by some amount that I don't know what they are. And so at equilibrium, I would say I have X and X for the concentrations of those. Now notice I did use those all in a 1-to-1-to-1 ratio because my coefficients here are 1-to-1-to-1. So now what I need to do is utilize this Ka value, this equilibrium constant, in order to try and solve these ion concentrations here. And you're thinking, well, why do we want those ion concentrations? Well, think about the goal of what we're trying to solve here. We're trying to get to pH. And I know that if I either have H+ or hydronium ion concentration, that I can use that with a pH calculation in order to solve what that pH would be. And so that's kind of the eventual goal here, is that I want to solve X so then I can use X in a pH calculation. And so to do that, I want to first think about that equilibrium expression for my substance. And so just like we've done before, I would have that my Ka is equal to my two products raised to their coefficients. So the hydronium and the acetate would be raised to 1 and 1 over my reactant of the original acetic acid. Again, notice I did not include water in here because, again, it is a pure liquid. And so then, just like we've done before, I plugged in everything into that Ka expression that I know, along with the Ka value that they gave me in the problem, that 1.8 times 10 to the negative fifth. That got what I wrote here in dark blue. And upon first glance, it looks like, ooh, that would be kind of tricky to solve algebra-wise. I have x squared on top, but I have minus x on the bottom. And so I would have two different exponents for x. I can't just square root both sides to solve it. That looks like it would be kind of tricky. Well, I'm going to give you a secret here. Almost all of your Ka or Kb values are going to be incredibly small. And because of that, remember, we get to ignore that loss that the 2.50 would have had because so little of it is being lost. It's where we joked about if I have $100 in the bank and I lose $1, I'm not going to say, oh, I have $99 in the bank. If somebody asks me, I'm just going to be like, oh, I have right around $100 in the bank. That loss, what I'm losing, is so minor that in the grand scheme of this, it doesn't even matter. So I put that I'm going to ignore that because I had a very small Ka value. So then my goal is to solve for x. And once I get rid of that minus x down there, you can see that really simplifies things. So I would want to multiply over that 2.50, but then I also want to get rid of the x squared. So I would square root both sides. And so that would end up here with this value solving for x. And once I plugged all of that math into my calculator, I got x equaling 0.0067. Now, once I get this value, I want to ask myself, okay, what does this represent? Well, this represents two things. This represents the amount of acetate concentration I would have at equilibrium, and it also represents the concentration of hydronium ion that I would have at equilibrium. Now, technically, it also represents the loss here on the acetic acid, but remember, this is so small that by the time I subtract it off of the 2.50, you basically round right back up to 2.50, so in the grand scheme of it, it doesn't even matter. The key thing though here for us is that that X represented that hydronium. Why is that important? Well, think about what I'm trying to solve. I'm trying to get to pH. And so now that I know that hydronium, which is the same thing as writing H+, is equal to that 0.0067, I now can take the negative log of that value and solve for pH. So I would take the negative log of that 0.0067, and that would get me a pH value of 2.17. By the way, a quick mention on Sig Figs here. You notice back over here with all this math, I only showed 2 significant figures because the Ka value they gave me only had 2 significant figures. But then when I got up here and I had 2 Sig Figs, remember when I take the negative log of it, those 2 Sig Figs would represent 2 places past the decimal on the pH. So whenever I do those power values, remember the number of significant figures are only the ones past the decimal. So now that I have pH, I can also solve my percent ionization. So to do that, the formula we would use, since this was an acid, is that we would take our H+ concentration, divide it by the original acid concentration, and times it by 100 to get that fraction into percent. So my 0.0067, I would divide that by the original concentration of 2.50 that I had, multiply by 100, and then therefore that would get me my percent ionization of 0.27%. So again, you can see it was super small, very little of that original acid actually changed over into ions. Most of it, 99.7% of it, stayed as the original substance. All right, let's go ahead and flip the page and see one that is a base. All right, so on this problem here, it says, what is the pH and percent ionization of a 0.250 molar aqueous ammonia solution? Kb of ammonia is 1.8 times 10 in the -5th. And I noticed a few things off the bat. First off, they give me a Kb value here for ammonia. So that means there's 2 things I know. Number 1, ammonia must be a base, and so therefore it's going to accept a proton. But I also know that it must be a weak base because it has a Kb value. So when I start writing out my Rice table, I want to make sure in my reaction that I address the fact that that NH3 would end up accepting that proton. Now, it wants me to eventually solve pH and percent ionization, just like we saw in the problem before. And so I know in order to get the correct ion concentrations, I'm going to need to utilize an equilibrium expression in order to be able to do that. So the Rice table here is going to need to be part of my work. So the first thing I did is address the reaction. Now for NH3 to gain a proton, I know that I'm going to have to put this with water. Anytime I have those weak bases, I have to show water in this dissociation equation. And so the NH3 would accept a proton, accept an H+ from the water. That would leave behind from the water OH -1, so hydroxide would be the conjugate base of the water acting as the acid here. Ammonium would end up getting created when the NH3, the base, gains the proton to make the conjugate acid here. So then, in continuing to fill out my Rice table, it told me that initially I had 0.250 molarity of the ammonia. Initially, before I did any kind of ionization, I would have had 0 for hydroxide and 0 for the ammonium. Then I would have said, hey, that NH3, that's going to have to go down by some amount. I know it's not going to completely go away because this is weak, but I know that the hydroxide and the ammonium would go up by that same amount. And so just like we did before, I would now utilize my equilibrium expression in order to be able to solve this problem. Again, notice I did not include water here because, again, it's a pure liquid. So when I wrote my Kb expression here, first off, notice I did put Kb instead of Ka since it was a base, but I did my products over my reactant just like I did before. And what's interesting about this one is that the Kb value was actually the same as the Ka of acetic. That is just a coincidence. Often those numbers are given to you and they could be any kind of various number. So just a sheer coincidence that the Kb here was the same as the Ka value on acetic. Again, I get to the point here where I have that minus X, but this is incredibly small for that Kb value, so I get to ignore that change. And so then I would work to solve X. So I would bring the 0.250 to the other side by multiplying it To undo the squared, I would have square rooted both sides, and that eventually gets my x being 0.0021. Now, here's where the key difference is between the acid problems and the base problems. With an acid, when I solved that x, that was equal to hydrogen ion concentration up here because that's what I ended up creating when it ionized. But here, because this is a base, I'm not making H plus or hydronium, I'm making hydroxide. And so that's going to really change what we're doing as far as our calculations here in a moment. Now, did we also make that 0.0021 molarity of the ammonium polyatomic ion? Absolutely. But more importantly, we made 0.0021 molarity of hydroxide. And I know if I have hydroxide that I eventually could solve pH. And so here what I would do is I would take the negative log of that hydroxide, which would get me the pOH. Now be careful. I see a lot of people want to stop here and think that this is their pH. But think about, does that make sense for something that we know is a base? Of course, that does not make sense for the pH, and that is because it is the pOH. We know that the pH of a base needs to be above 7, just like the pH of an acid on our previous problem needed to be below 7. And so what I would need to do then is I would need to use that second formula, that pH plus pOH equals 14. So if I take 14 and subtract that pOH, then I can get my pH. And 11.32 definitely makes sense for something that is a base. So always ask yourself, does your ending pH make sense for what kind of substance you have? If it's an acid, it should be below 7. If it's a base, it should be above 7. And if not, then that might mean you need to do a second calculation like you do here on these base problems. So be very careful in the base ones. You're going to need to do 2 pH, pOH calculations, whereas with the acid problems, you only needed to do 1. Now, once I have that pH, I can now work to solve my percent ionization. Here, what would happen is your percent ionization would be your hydroxide over that original ammonia times 100, so 0.0021 over the 0.250 times 100 to give 0.84% for the ionization. So again, incredibly small, just like we saw a minute ago. Now, let's talk about changes in percent ionization for just a moment. So first off, let's think about the situation where we have two solutions that have the same exact molarity, maybe two acids that are both 1.0 molar, but they have different Ka or Kb values from each other. So maybe one of the acids has a larger Ka than the other one. Think about what a larger Ka value would mean. That would mean that a little bit more of that is becoming product than the other substance. So in that particular substance, the equilibrium is a little bit more product favored. Well, when you're thinking about these equilibrium setups, all of these are the original acid or base becoming ions. And so what that larger Ka or Kb value would mean is that more ions are being made. Now, if more ions are being made, but I'm starting off with that same total molarity of the acid or base, then that would indicate a greater percent ionization, and that would also indicate that that acid or base is stronger than the other one. Not strong enough to make it on the strong list of acids or bases, but we can have a stronger weak acid or base than something else. And we're going to actually talk a little bit more about this topic on another day. But the other situation I want to talk about is if a solution has its molarity changed. So let's say that I have an acid that has a particular molarity and a particular Ka value, but I end up diluting everything, maybe adding water, or maybe I remove water and make it more concentrated. Because I haven't changed temperature, that equilibrium constant, that K or Kb value, should be exactly the same. But when I add or remove that water, when I change that molarity, I'm changing it from being that K value. So now I've changed to some new Q value. So for example, let's say if a solution is diluted, what that would mean is that all my molarity values decrease. And if I'm thinking, say, maybe for an acid, like a Ka here, that would mean that my ions over my original acid, that each of these concentrations will decrease. Well, here's the issue though. The two ions being on top, that decrease is going to basically happen double, whereas in the denominator, it only happens once. And so what happens is that the numerator changes more than the denominator when I'm thinking about those Ka and Kb expressions. Now, in the case of the molarity values decreasing, that would cause the Q to be less than the K at that point. And so what I would need to do is shift things around in order to get Q back equal to K. And in this instance, that would cause the reaction to shift to the product side to reestablish equilibrium. And remember, the products are those ions, and so as more ions are getting made, that would lead to a greater percent dissociation. Now think about how unusual that is. That means that percent ionization increases as the molarity of the acid or base decreases. On the flip side, if I increase molarity, that would decrease percent ionization, which seems very unusual because you're like, well, if I, have a higher molarity, doesn't that mean I make more ions? Or if I have a lower molarity, wouldn't that make me have less ions? Yes, but the problem is that the numerator and the denominator aren't changing proportionally. And so that's going to end up kind of making those ratios not be quite what we expect them to be. So I'm going to kind of show you this from a numerical standpoint to kind of prove to you that this actually is a thing that happens. And so what I want to do is I want to actually compare the first calculation that we did on the first page. So with that acetic acid, we had 2.50 molarity, and you notice that it had a pH of 2.17 and a percent ionization of 0.27%. I'm going to actually show you, if I change that molarity, what that does to these numbers. So what I did is I reworked this entire problem from the first page, only instead of using 2.50 molarity, I used 3.50 molarity. So this is the same exact problem, except I used 3.50 molar. And you notice that the pH, which was originally 2.17, is now 2.10. The percent ionization that was 0.27% is now 0.23%. So different than what we saw with the 2.50 molar, now that we have 3.50 molar. So now think about what's happening here, okay? I increased molarity for this example, okay? I went from 2.50 molar to 3.50 molar, which means I had more hydrogen ions. So does it make sense for this pH to be a little bit lower than the other one we saw? Absolutely. If the molarity was greater, then I should be making more of those hydrogen ions. However, notice that the percent dissociation actually decreased. Okay, the original one was 0.27 and this is 0.23. So even though I had an increase in that molarity in the denominator, what is happening is that I'm not getting an equal change in both numerator and denominator here. So even though these numbers, both on top and bottom, are bigger, the percent actually comes out smaller. I'm not getting the same rate of change happening in both reactants and products here. So you've got to be really, really careful. Even though I've increased that molarity, I actually decreased my percent ionization here, which is a little bit counterintuitive to what most people think. So be very careful on that situation. You want to remember that as percent ionization increases, as molarity decreases, or if I increase molarity, that would decrease that percent ionization. So again, those work kind of opposite of each other as far as those trends are concerned. All right, I hope you're feeling good about calculations involving weak acids and bases, as well as the idea of percent ionization. If you have any questions or need any help, please feel free to email me. Bye, guys.